Okay, for the next problem, we want to consider the integral from 0 to 5 of 4 pi x to the 10th dx. So if this is a disk integral with the axis y equals 0, let's describe the region that's being revolved. So if this is a disk integral with the axis y equals 0, in other words, if what we're doing is we're taking some function and revolving it around the x-axis on the interval 0 to 5, then the question is, what function is this? Well, we can sort of back into what the answer is, because what we know is that the volume must be equal to pi. It must be, well, actually, let's keep the pi on one side of the equation. It must be equal to the integral from 0 to 5 of pi times f of x squared dx. In other words, that's what would happen if we had this region and revolved it around the x-axis. If this was f of x, we would be forming exactly this as the disk integral. So what that means is that this must be equal to the integral from 0 to 5 of 4 pi x to the 10th dx. That means that we can actually equate this and this, because we're integrating the same thing. These must be the same. So if pi f of x squared dx equals 4 pi x to the 10th dx, let's look at what we can cancel out. We can cancel out the dx's because they're the same on both sides. We can cancel out the pi's, and that's going to give us f of x squared equals 4x to the 10th, so I get f of x equals 2x to the 5th. So the region being revolved is just going to be the region below, that's not what x to the 5th looks like, let's draw it realistically, is the region below y equals y equals 2x to the 5th on the interval 0, 5. That's the region that's being revolved. And we could describe that in words. We could say the region bounded by the x-axis, the line x equals 5, and the curve y equals 2x to the 5th. I'm not going to write out all the words, but you could say that it's bounded on three sides by those curves and lines. Okay. So now let's take the same integral. Let me just write that integral again. Integral 4 pi x to the 10th dx from 0 to 5. And suppose that we're now interpreting this as a shell integral. Well, it's basically the same issue. So I have some function, f of x, on the interval 0 to 5, and now I'm revolving it around the line x equals 0, which is the y-axis. Well, if I'm doing that, then the volume of the volume of an integral that looks like this with the axis x equals 0 is going to be given by the integral from 0 to 5 of 2 pi times x f of x dx. How do we know that? Because we know how to form a shell integral. This is the radius. I know I've put the 2 pi back inside the integral, but it doesn't matter. It's just a constant that we're multiplying by. We know that this is going to be the height, and we know they both have a dx. So once again, I can simply equate these. This is going to be the integral from 0 to 5 of 4 pi x to the 10th dx. So let's equate the expressions inside the integral and say 2 pi x f of x dx equals 4 pi x to the 10th dx. So again, I'm going to cancel the things that I can cancel. The pi's cancel, the dx's cancel. I meant to do that in red. And in fact, the 2 and the 4 cancel a little bit because I can just rewrite that. If I divide both sides by 2, the 2 disappears on the left and the 4 becomes a 2 on the right. So now I have is x f of x equals 2x to the 10th. So I can actually cancel a factor of x, giving me f of x. F of x equals 2x to the 9th. So there we go. That means that the region is actually going to be 2x to the 9th. I know I'm not anywhere near drawing this to scale, so that's y equals 2x to the 9th on the interval 0 to 5. And I'm revolving this around the y-axis. So this is the region bounded on three sides by the x-axis, the line y equals 2x to the ninth, and the line x equals 5. So that's a description of this region. So it's kind of interesting is I can take the same integral, and depending on whether it's a shell integral or a disk integral, I can interpret it two ways. Or for that matter, there's no reason I can't just interpret this as the area under the curve y equals 4 pi x to the 10th on the interval 0 to 5. Integrals aren't area integrals or volume integrals or shell integrals or disk integrals. They're just integrals. How we interpret them is up to the geometry that we impose on them. We form them from a particular geometry. We can interpret the same integral in accordance with different geometries.